So this is my code in which I'm going to generate some sequences of random numbers. And I'm just importing NumPy and Matplotlib so I can use some arrays and I can make some plots. That's what I'm doing here. And then I'm going to just explore some different cases of the parameter space of our random number generator. And so that I could remember them, I've stuck them all in here. Let me go down to these guys. So there's three different values of the parameters M, A, and C here that I picked to kind of illustrate some of the flaws in this random number generating scheme, right? Because actually that if you just go and pick your own favorite M, A, and C, you're probably going to have a flaw. Most sets of numbers will have kind of flawed random number generation. So I just want to show you some of the common flaws, and then we'll talk about the standard ways to get around the worst flaws. So let's go here and define the three parameters of the random number generator. And then a X here is the seed value. And here I'm just picking, so the multiplier, I've got 1. I've got, for the constant, I've got 1. And for the divider, I've got 100. So let's see what happens if we do that. I'm going to plot here. So I ran many cases of this, generating streams of random numbers. And now I'm just going to plot them. And what I'm plotting here horizontally is the kind of the label or the index of the random number. So this is, think of X subscript n. I'm plotting the value of n. So I started with x0, then x1, and x2, up to 1,000 here. So this is my label on my stream of random numbers. And then vertically, I'm plotting the random number itself, starting from the seed value. If we go back up here, I don't know if I said the seed value was 47. For some reason I picked that. Well, if you look at this pattern, right, this doesn't look like a random number sequence, right? And what have we just built? We've just built a little algorithm, just basically increments the prior number for the next number. Our multiplier was 1. So we're going to multiply the prior number by 1. That was A. And we're going to add 1. So we're just going that choice of A and C is just incrementing the number. That will, when we calculate the remainder by division by n was 100. So that remainder will keep incrementing until you get to 100, and then it'll be reset back to 0. And so all we've done is calculate by this choice of parameters is obtained a algorithm, recursive algorithm that increments from 0 to 100 and back to 0 and up to 100 and so on and so forth. So this is clearly not as a random good random number sequence. So that's just to show you that, within this algorithm are really flawed pathological parameters for trying to generate random numbers. This is obviously not good. Let's reject that one. I got a second example here. Okay, so in this one, so I'm playing around. I've realized, well, I don't want to multiply by 1. So multiplying by 1 is a really bad idea because, if you add 1, you're increment by 1. If you added 2, you'd be incrementing by 2. You're just building an incrementer. So let's multiply by a bigger number. So here I'm multiplying by 7. That's the multiplier. I'm not adding a constant. And I'm going to generate numbers up to 31. So I'll be able to generate random numbers in a range from 0 to 31 because my M is 32. Okay, so let's plot this guy. Let's plot this guy on a different range. I'm just going to plot, say, the first 100. So this is the output of this random number generator, which also isn't very random at all. Remember, we got a space of 32 numbers from 0 to 31. But actually, we're only ever generating one of 4 of them. So we generate 0s and 7s and 17s and 23s, I think. And there's a very short period here as we walk through, and we're always walking through 1 to 7 to 17 to 23, and then we go back to 1. So this is an example where this choice, it wasn't a simple incrementer, but this choice of random number generator parameters has a much shorter period than we want. So, you try and pick random number parameters that will give you the period that's allowed by the value of M, the divider. And so we had a value of M that was 32, but we're not using hardly any of that range. There's a very short period. So that's another sort of fatal flaw that just kind of randomly picking random numbers can create. Let me show you one more common flaw. So here's another set of random numbers I picked. I just changed the multiplier, basically, from the previous one. See if it was a problem with the multiplier. And so let's go ahead and take a look at this one. And so here's the pattern for this one. Maybe this one, let me print out. The numbers, so I can better show you the problem with this one. And I'll just print out some handful of them. So this one also has a fairly short period compared to the period that I would hope, which would correspond to the M value. But it was better than the last choice. But this one also has another flaw that wasn't really apparent in the last choice. Look how the numbers are incrementing. So we start with 1 and we go to 5, we add 4. Over here, this next pair, 25 to 29, we add 4. This next pair, 17 to 21, we add 4. So we've just built a sequence of pairs of numbers where we're adding 4. So here the problem is, well, it's a shorter period than we wanted, but also the incrementing. We got back to a problem of incrementing by units again. So I just wanted to show you those to give you, the sense that it's actually quite difficult to, and there's a lot of work on finding the best numbers to use for this, this algorithm to generate at least reasonable randomness. And, you know, you might want to play this sort of playing around is best, you know, just play around yourself, think about your own sort of numbers and see how easy, or it's surprisingly hard to actually generate random numbers with this random number generator. In fact, I tried it with relatively small numbers. I was completely unsuccessful in making it generate what seemed like random numbers. So I'm going to go back to the slides. We've looked at these flaws. So there are some rules for generating reasonable sequences of random numbers. Specifically, there are rules, these rules I'm written down here are for generating a sequence of numbers that uses the sort of full period as determined by the parameter n. So you couldn't beat that. So these are the rules for generating the full periods specified by n. I should say that the periods I used 100 because it's you know it's a round number. I used 32 because I was thinking of computers like, you know, bits, and so a power of 2 makes sense on a computer, and that's actually a reasonable philosophy. So the older computers, when this method was used, might have used 2 to the power 16. They had 16 bits for a word in the computer. And then it became 2 to the power 32, and even 2 to the power 64 is used for this type of random number generators. So those are the actual values of n, not these kindergarten values that I was picking so that we could look at the numbers. But anyway, we want to use, if we use 2 to the 16 or 2 to the 32 or 2 to the 64, we want to pick the other parameters, the multiplier and the constant, so that we get the full range, the full period that's potentially available from that large divider. So the rules are these 3 rules here. So one rule is that M and C, by the way, I'm not going to, I mean, I don't know how to prove these rules. I don't know how to derive these rules. These rules have been proved and derived, and we're just going to take a look at them. So one rule is that M and C are coprimes. What that means is, if 2 numbers are coprimes, they don't have a common factor other than 1. So that it doesn't mean that they both have to be primes. It just means that they can't have a common factor other than 1. So that's a rule. And then there's a couple of the next 2 rules kind of are sort of focus on the multiplier. So the second rule is that the multiplier -1 must be divisible by any prime factors of any prime factors of n. So supposing I was picking 2 to the 16, 2 to the 32, 2 to the 64, my prime factor would be a 2. And so a -1 must be divisible by 2. So I could have 3 for a, I could have 5 or 7, or, you know, in reality, some big number that a -1 is divisible by 2. So that's another rule. And then the last rule is that if m is a multiple of 4, and the m's we're talking about, 2 to the 16, 2 to the 32, 2 to the 64, divisible by 4, then a-1 must also be divisible by 4. So those are 3 rules. And so let me show you an example. So where I'm going to try to obey those rules. And as I say, if I obey those rules, I should get the full period. Now I'll show you the rules for a full period where the divider is a small number, so we can see it. I'll make it 8. But we should at least get the full period of 8, which we never managed to do in those first examples that I picked.
What's a full period?
The full period is, so supposing I pick 8, it's mean that your stream of random numbers will pick every number from 0 to 7 before starting to repeat. So, yeah, in the prior examples I showed you, the two that had m equals 32. So I showed you 2 examples with m equals 32, but they didn't have the full period. They didn't give you every number from 0 to 31 before they started to repeat. They had much shorter periods. I think one had 4. Did one have 2 or something? I can't remember. They had much shorter periods. So if I was using m equals 32 and I wanted a full period, I would get all 31 numbers from 0 to 31. Don't want them incrementally, but just jumbled around before I start to repeat. So that's a full period. And so you want that because you want to be able to generate a stream of random numbers, a long stream of random numbers. If you're doing a model simulation, you're going to be calling this many, 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 many times. And so you want a long stream. Okay, so now I'm going to go back here. And I got some examples of full period. So here, my value of, in this line here, my value of m is 8. So the best I can do is have a period, a full period that has the 8 different values from 0 to 7 before it repeats. If you look at, I'm just thinking about those three conditions, but I have problems remembering them all. So the first one was that M and C can't have are co-primes, so they can't have a common factor. Well, C is 1, and M is 8, so it has a prime factor 2, and so that's fulfilled. The other condition was really on A, that A minus 1 is divisible by the prime factors of M. So that's 2, and A minus 1. A is 5, so A minus 1 is 4, so that works. And then the other one, that if M is divisible by 4, A minus 1 is divisible by 4, and that's true too. So I did pick them according to that rule. So let's run this guy. And then let's take a look at this plot. And maybe, let me change the scale a bit on this. And maybe it's easier if I make this a line. Okay. So here you see the sequence of numbers. We're starting, my seed value is 4. I go 5, I go 2, I go 3, I go 0, 1, 6, 7. I get back to 4 over here. And so this fulfilled those conditions for getting the full period. And indeed, I got the full period. So that worked. I'll show you one more example. So again, I'm going to pick some para 2 because I'm thinking of computers. So M is 16. So if I want the full period, I want a period of the 16 numbers from 0 to 15. And I've got to choose my M and C such that they have no co-primes, so that they are co-primes, sorry. They don't have any common factors, and I've done that. So factor of 16 is 2, and my C is 3. So I picked something that wasn't 1, but it doesn't have a common co-prime, doesn't have a common factor with M. And then my A, I picked that as 5 again, just because we checked that right. 5 minus 1 is 4, it's divisible by 4, it's divisible by 2. So it fulfills the other conditions. And so here's my sequence. Remember, we expect to get, we want to get 16 different numbers. And so maybe we could look for where it repeats. Starts with 1. And I think we don't repeat until over there at 17. So we've got the 16 different numbers as we walk around. And so that also has fulfilled the full period. So that's how you would choose numbers to fulfill the full period. So this table just shows you, now these are real numbers that were used by real random number generators over the years that use this arithmetic approach to generating random numbers. So you see the M values, there's lots of 2 to the 32s, 2 to the 16, 2 to the 64. So that's kind of a natural number to be picking for a computer. And then you see, different combinations of A and C, which are picked to try and get as large a range as possible. Here is a set that, so this is, these numbers in that table are from glib, I think, or GCC. So I just picked those numbers, and I got another set of numbers in here that are from, what was the other? Numerical Recipes. You might know this famous book by Knuth that's Numerical Recipes. So he worked a lot on random numbers, and these were his favorite numbers, I guess. But anyway, so here's a set of random numbers. Sorry, here's a set of parameters for our random number generator, and we can try that out and make some plots for that. And so at this point, I'm going to show you a handful of plots that kind of allow us to test randomness a little more quantitatively than we've been doing so far. So our test of randomness so far are to generate numbers with a small enough period that we can just spot by eye that this looks bad or this looks okay. So if we're going to use larger values of n, we're going to need some more statistical ways of looking for flaws or evidence of non-randomness of our random numbers. Okay, so now I'm generating, let's see, 100,000 random numbers. I think I already did this, but. And we're going to make some plots. This plot here, where we just look at the sequence, is not great if you've got a large value of m and you want to calculate a big long string of random numbers. It's going to be really hard to see a problem in this plot. So that's a point I wanted to make. We use this plot, or we use just printing out the numbers. That's not going to work anymore. And so we'll see that. If I just remove this and plot points. here is the corresponding plot. So from 0 to 100,000 is an index for the random numbers, and then we're generating random numbers from 0 to, it was 2 to the 16, I think, this one. So this is where 2 to the 16 is. And we just filled up the space. So it's really hard to see whether, I mean, it looks sort of vaguely random because it's just magenta everywhere in the plot, but it's, you know, I think we're not statistically testing that it's random. Okay, so let's make some plots that might help us test randomness in a more quantitative way. So in this plot, I'm going to make a histogram. What I'm going to do is divide that range of possible random numbers from my random number generator. So that range was from 0 to 2 to the power 16 minus 1. I'm going to divide it into 32 separate intervals, each one of them 1/32 of that second of that entire range. And I'm just going to histogram how many times I got a random number in each of those intervals. So if it is random, then we should get equal statistically numbers of random numbers in the 32 intervals. So there'll be some noise on it because I've got a finite number of random numbers. I've got 100,000 random numbers, but within that statistics, I should see equal numbers in the 32 intervals. So to do this, I use the I used a function in NumPy that builds a histogram for me, and then I used a function in matplotlib that plots the histogram. So by building a histogram, I mean, I've got this kind of a big array of 100,000 random numbers, and I want to throw them into little bins, 32 separate bins, and count how many I get in each of the 32 bins. So this core to this NumPy histogram function is basically doing that. I'm giving it the array of 100,000 numbers, and then it's putting them in this 32 different bins. So just look at the arguments here. R is the array of 100,000 numbers, and then the number of bins is the number of intervals that I'm going to divide, equal sized intervals that I'm going to divide the range into. And so the quarter histogram literally makes the histogram for that. There are other arguments you can use the histogram function. It's quite handy sometimes. You can specify, I'm not specifying the range of the histogram here. It's getting the range from the data, but you can specify the range also with more parameters, like a lower limit and an upper limit. Okay, so this divides this makes a histogram out of the data, and it returns a couple of variables that the one that we'll work with. Let me just mention this. So this first argument that it returns YF, that is just the contents of each bit. And then the second argument, bins, tells us about the bin edges. I'm just going to plot YF, so the number of contents of the bin, versus the central value of each bin. And so I made the central values XF with that function we used before, linspace. So I'm going to divide the range of M, allowed range of M, into 32 bins. And I'm going to define XF as the center of each of those bins. That's that second line here. Couple more points. So the values of y, which are the number of entries in each bin, they're not going to be exactly the same. They have statistical fluctuations on them. And the statistical fluctuations are given by a normal distribution, Gaussian distribution. They'd be determined by the square root of the number of counts in the bin. And so I'm going to plot an error bar on the data points that corresponds to the square root of the number of counts in the bin. So if I had 100 counts in a bin, I could be plotting an error bar that's plus or minus 10. The function that I call to make the plot also wants the size of the error in the y-x direction horizontally, but that's you know, there is no error for us. These are just fixed bins of a certain size. So I set that to be 0. And then this is the plotting function I use. I don't think we talked about this one before, but it's called error bar. It's just another plotting function that's in matplotlib. It allows you to plot x versus y with the error bars on it. So that's kind of handy for this. And so here's the result. So we had 100,000 data points, had 100,000 random numbers, and we divided that range of them into 32. So expect something approximately 3,000 counts per histogram bit, which a little more than that, so, which is what we get. But I think you'll notice that the error bars that we're assigning them seem to be small compared to the scatter. That there is more scatter than you would expect for a truly random distribution. And so this is an indication that even this, even this sort of quote professional values for these this random number generator is not truly random. There are still hidden in that 100,000 numbers is still that problem of sequences in the data, common sequences in the data. And I think that's the heart of this. So, yeah.
Can you go over the bit where you talk about the central value in each bin?
Yeah, so I said for this plot, I made 100,000 random numbers. And then I'm going to plot the occurrences of different random numbers in 32 different bins from 0 to the maximum, 2 to the 16 minus 1. So any one of those bins should have 1/32 of the random numbers in it. And 1/32 of 100,000 is roughly this 3,000.
So what was the central value?
The central value of x, I just made the central value, see this is a scale from 0 to this number that is a bit bigger than 2 times 10 to the 9. 2 times, if you figure out what 2 to the 16 is, then it corresponds to that full range there. And so I you know, this is giving us numbers over the full range of m. And I'm just looking at if I divide that full range into 32, you know, how many fall in each of those little windows, each of those little bits. Yeah.
So just to make sure I understand, so like the XF, the reason that you go from 0.5 to n minus 0.5, just you're cutting that bit of the one, putting it in the center of.
Yeah, what did I do that? So I start from a I don't think I can't remember why I did that. I think the reason I did that is that's ridiculous for this value of m, right? The value of m is 2 to the power 16. The half and the minus a half, that's ridiculous. I think I've got it there when I put in, say, 32. or some small number of m. It was kind of to line up the bin centers, right? So, but now it's just confusing. Why would I have done that? But if you put in 32, I think it becomes obvious. But it's the point you said. Yeah, I want it to be at just to mark. Yeah, the centers of the bins. Okay, so that showed up some flaws. This is a famous plot that also shows up some flaws. I don't think it shows them up very clearly in this case because I haven't generated a rough. You have to generate a lot of random numbers for this. Let me show you this one for a different example. Oh yeah, so that's why I put these here. Okay, so here's a set of numbers. Again, the range here is small, right? M is 31. I'm only picking this set or this other set that I got here to show you the spectral test, which is actually a very rigorous test of the randomness of these numbers, specifically these patterns that consecutive numbers can have and things like that. So the spectral test is used to test that. We could do it for our 2 to the power 16 value of m. We have to generate a huge number of random numbers and then kind of blow up a small space in this spectral test. So it would be here all night.
What if we try to Fourier transform the data and look for the frequencies? Would that be
Oh, that's an interesting idea. Yeah, I don't know what. That's an interesting idea. You know, I don't know the answer to that. You should try it. You should try it, and then you can give the class on the Fourier transform of the random numbers. Yeah, it'd be really interesting to know. Okay, so I wanted to show you this other test. It's called a spectral test. It's where you plot x. So I'm plotting here xn minus xn minus 1. So it's a plot of, two adjacent numbers. So you might think, well, look, if you plot the one number versus the prior number in sort of on a two-dimensional plane, you can get you can be anywhere on this space if you've got a good set of random numbers. But this type of generator has flaws that always show up in this type of plot. So as an example, right here, so my numbers, m is 31 in this case. So we should be able to generate numbers from 0 to 30 along the horizontal axis, that's xn, and along the vertical axis, that's xn minus 1. What you see here, I'm generating a lot of different numbers. I think I generate all the numbers from 0 to 30, if you look horizontally. But there's a pattern between xn and xn minus 1. You can see these planes. So these are called hyperplanes. You can plot this in 3 dimensions too. If you do xn minus xn minus 1, minus and xn minus 2, then so these are hyperlines. So you get hypersurfaces or hyperplanes if you do 3 dimensions. So this is very typical of this type of random number generator, that in this space that should just be occupied, filled up with points, you get these planes. You get lines in the two-dimensional plot, you get planes in the three-dimensional plot. And the quality of the randomness is often assessed by the closer the planes are, the more random it is. The further apart the planes are, the less random it is. That's why I wanted to show you one other case up here. So this is a different set of parameters. Well, actually, the only number I changed is the multiplier. It's gone from 3 to 13. And let's make that spectral plot. And so here you see a different set of planes. Now the steeper, the distance between them is a little less. And so this would be considered a bit better than the prior case. So this is another important test that is done on this type of random number generator. Okay. I want to just show you one last thing, I promise. I'm going to go back to that 2 to the 16 one thing. The last test I wanted to show you was a kind of chi-squared test. So this really goes with this plot here. You can evaluate, so in that plot, within the error bars, we should have the same number of counts in each of the 32 bins. And so you can calculate a chi-squared for those 32 points. The chi-squared is basically if you take the mean of this, calculate the mean in each bin, calculate the mean through all the 32 bins, and then you do the difference from the mean, you square that, you divide by the uncertainty on each of the uncertainty squared on each data point, and add that up for all the data points. That's the chi-squared. And so calculating the chi-squared is a chi-squared test. If there's if the fluctuations are consistent with statistics, then you should just get a chi-squared of 1 when you sum the differences squared divided by the uncertainties on them squared. If you get something that's much bigger than 1, it says you're seeing more scatter than you should statistically get. So it breaks randomness in some way. If you got it much smaller than 1, it would also say that you've got a result that's much smaller than the statistical variations you expect. That would also break randomness. And so here, I'm just calculating the mean of those 32 points. Those were the YFs. And then I'm calculating the differences of each point from the mean squared divided by the errors on them squared. I'm adding all that up, I'm summing it up, divided by the number of degrees of freedom, which is the number of points minus 1. That gives me the chi-squared. So this here is the chi-squared test. And then I'm just printing out the values in my calculations. So the mean was 3,125. If you remember that plot, that's roughly where the mean was. And that's, 1/32 of the 100,000. The chi-squared, so this measures the variations in units of the uncertainties on the points. This chi-squared is much bigger than 1. And so it's quantifying what we saw by eye. The fluctuations of the data around the mean are much bigger than the statistical variations would say, or the statistics would say. And so that's why I got, a number that's way bigger than 1. And so that's a final test that I wanted to describe. Any questions on all that?
So when you showed the error bars, so the degree of randomness there would show that, I mean, the more randomness would mean longer error bars.
Yeah, let me go back to that. I should have done I should have done the chi-square test immediately after this histogram test. For some reason, I had the spectral test in there. I'm sorry about that. That was a bit confusing. But yeah, these error bars. So look, we got about 3,000 entries in a bin. So if you take the square root of 3,000, so square root of 20 times 20 that's 400. The square root of 3,000. 50. I can't stand up here and do math. But anyway, the error bars are the square roots of those numbers, and that should indicate the fluctuations. So these fluctuations are much bigger than the statistical error bars, which is indicating, some non-statistical distribution here.
So the statistical error bars would be just root n.
Yeah, just square root of n.
Larger than that.
And these fluctuations are much larger than that. So look, you could get both with this type of random number generator. Let me give you an example. That very first example that we wrote down, where we had A and C equal 1, that just built an incrementer. So it just counted through, right? Well, that would generate random numbers, equal numbers of random numbers in each bit. I wouldn't even have any statistical fluctuations on it. So that would show up in a chi-square test of being too small a chi-square. Another example, the second example we did, I can't remember the values we put in, but remember we put in some values and we had a much shorter period than the true period, which meant that we weren't using some numbers and we were using other numbers. If you made a histogram of that, you'd find big holes, you'd find much bigger fluctuations. So the chi-square test is sensitive to both of those problems. Building something that just walks systematically through the numbers versus building something that hops over certain numbers or ranges of numbers. And so I think if you're getting a chi-square bigger than 1, it's probably telling you you've got some holes in your distribution where you're not accessing them with your parameter space. And I think if you've got a chi-square that's much smaller than 1, it's telling you you've built some sort of incrementer that's equally walking through the data points. And those are two big flaws in this arithmetic random number generator.